There's all sorts of different ways to come up with data points to suggest how long something's been there, or how long it's been mineralizing, or how long it's been fossilized, whatever you want to call it. And so what we hear all the time, and we've touched on this in past podcasts, the radiometric dating method we hear from middle school is carbon dating.
Yep.
And we hear that once in 8th grade, and we don't take AP chemistry or anything after that to learn anything more. We hear carbon dating, and that's all we've known, that's all we've been told, that's all we understand to exist. But there are dozens of other radiometric dating methods, like you just mentioned, that isotopes between one bit of let's say iron and another piece of iron, it could be like 204 and 207. There's other methods for timescales. Carbon dating can be tough. It can be tainted or not as pure because of it's a very sensitive method to use, and it's accurate at its best out to a few thousand.
50,000 years,
50,000
more or less, right? Yeah. After that, it's very difficult to measure the amounts of surviving carbon-14. Yeah.
Exactly. So you wouldn't apply carbon dating to Dipsy's tibia here. It's way too old. So what would you apply to it?
You use a number of different elements depending on sort of what time frame you're looking at. Mostly it has to do with the length of the half-life, right? Mm-hmm. So for things like I said on the scale of hundreds of thousands, something like uranium thorium is a pretty common one. Going further back, I mean, there's potassium argon. I forget sort of what time scale that's used for, but I know some of the oldest ones are actually types of lead that have extraordinarily long half-lives, but will very slowly radioactively decay. And those are the sorts of elements they use to measure the age of the Earth, basically since the planet formed.
These windows, we estimate the age of the universe to be between like 14.3 and 14.7, somewhere in there. There's 200 million years on either side. That's the
confidence interval, the percent,
the margin of error, basically.
Yeah. Mm-hmm.
And you're like, 200 million years of a margin of error?
That's huge.
Just quacky science. That's crazy. I did the math on this, and the 200 million year margin of error at 14.5 billion years is like a margin of error of 0.0001%. It's 200 million years sounds like a whole lot, but at that time scale,
you're measuring such a big number.
Now you got to think about this. Now I attach it to my mind to an engineer and architect building a skyscraper. Mm-hmm. You cannot have massive margins of error when you're building a structure 1,500 feet tall. The margin of error at the base has to be the same margin of error within this tolerance that's insanely small to ensure that building
is actually straight up and down and doesn't fall over, and
Right. So for the universe to be this old and have that narrow of a margin of error is like that makes sense. Why wouldn't it? If we're sitting here talking today, we're talking about radiometric dating. We're a species that we're getting a little heady here. We're self-aware, self-conscious to look at the stars and say, what are those?
How long have those been here? A lot longer than you or I, at least.
Exactly. And then if we have these materials on Earth, we make rockets and we send probes out there to figure out what all this stuff is. We build telescopes and Galileo looking at these things. Like, it's when you're talking about these time scales and the Earth could be 4.5 billion or 4.4 billion or 4.3, 4.5, 4.6. And matter of fact, when you do the radiometric dating, you get these data points that have this kind of margin of error of a few million years or 100 million years.
Yep.
But that is such a tight tolerance. The best engineers in the world making like car engines and the SpaceX rockets and things like that, they're probably operating within margins that aren't too far off, or maybe even a little sloppier than that margin of error of the universe. Well, the light turned off, so that might be a
good stopping point.